So, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. This afternoon, we have Dr. Wang as a speaker. Dr. Wang studied at the Beijing Normal University and did his PhD there in astronomy in 2020, and is currently a postdoc at the University of KwaZulu-Natal, where he's working with Professor Ying-She Ma. Yeah, and thanks to Ying-She Ma, he's here this afternoon. Yeah. So, Dr. Wang, without further ado, you're most welcome to start your interesting lecture. Thank you very much for joining us this afternoon.
Yeah? Thank you. Thank you so much. Good afternoon, everyone. My name is Guo-Jian Wang. I'm a postdoc of the University of KwaZulu-Natal. It's my great honor to be here to give a talk, to share my study, my research, and to share my thoughts about the machine learning in cosmology and astrophysics. Thanks for the invitation and thanks for the organizer. Okay. The title here is the machine learning in cosmology and astrophysics. This is based on my research and my thoughts. So, here's a collection of my collaborators, and you see Professor Ying-She Ma here and other collaborators. So, okay. Here's an outline of my talk. The first part, I will give you a background of my research, and which includes the background of cosmology and some basic knowledge of machine learning. And the second part is focused on the foreground subtraction using machine learning. And the third part is focused on the parameter estimation using machine learning. And finally, I will give a summary. Okay, let's start from the cosmology. So what's the cosmology, and what do we study in cosmology? In cosmology, we studied of the large-scale structure of universe and the probability of the universe and the evolution of it. So, for example, we also study the origin of the universe and the fate of it, and what the universe is made of, and what's the component of it, and what's the law of the that governs the universe, and all of these are questions we want to know. So, in a word, we started to understand the origin, the structure, and evolution, and the fate of the universe. So, for example, for this picture, this is a history of the universe. So we know it starts from the Big Bang, and it evolves with the time, and finally we finally we can evolve the until what do we see today? Okay, for the universe, we want to say what it consists of. So for for the universe that we know today, it consists of there are three main parts. The first part is the normal matter. What's in normal matter? The disk here and the building here and all of that here are normal matter, and all the planets, all the stars, all the gas and in the universe are the normal matter. So all of these are all normal matter, and the combination of this are only 5% of the 5% of the matter in the universe. So which means that we only know 5% of the matter in the universe, and the other set, the other parts, more than 95% of it we don't know. And for dark matter, it's make up more than 20%, and we still don't know what it is, and maybe maybe everyone of us are maybe dark matter are around of us, and we don't know it. And the other part is the dark energy. Dark energy is they are more than 70% of it, and it plays a significant role in the evolution of the cosmology of the universe. And it's a still mystery, and we don't know what it is. So I don't know the knowing the components of the universe, and we can model the universe, and we have a list of parameters describing the components of the matter, and this is a so-called lambda CDM model. The lambda is called the dark energy, and the cold dark matter is the CDM, and this is a universe we know today. So for the universe, what we observe, you can see from the beginning of the time and to the present of the today, we can observe there are a lot of observations we can observe. So the first one is you can say we can observe the temperature fluctuation of the microwave background radiation. This is a very baby phase of the universe. It's very when the universe is very young, and we can also measure the intergalactic gas distribution, and in the near universe, local universe, we can observe the galaxy. We can count the galaxy. This is a galaxy, and that is galaxy. We can finally we can obtain a map of the galaxy. So there are a lot of information that we can observe of the universe. So with the we have a lot of telescopes to observe the universe, and with time going on, we can obtain a lot of data, and with the data we can obtain more and more data with the time goes on. So there is a problem here to be of the observation. So facing the big data, how can we deal with the so big data and extract more useful physical information from the data? This is a problem we are facing for the research of cosmology and astrophysics, and using a wider range of the astronomy. So all you may hear about the machine learning. Machine learning may be a better way to deal with the big data, and so what is machine learning? This is a picture this is the question I asked the ChatGPT. You know, ChatGPT is a chatbot. It's a big language model, and it can answer many questions of you. And I asked it what is machine learning, and I obtained a quite answer. It's that machine learning is a subfield of artificial intelligence (AI), and that focuses on the development of algorithms and statistical models that enable computer system to learn and improve the performance on specific tasks. So machine learning can allow computer to learn from data, learn knowledge from data, and make predictions from the based on the learned data. So there are several components of about the machine learning. The first one is the data. You know, the data is the represents the knowledge. So the machine should be trained on specific data. So this is the knowledge he learned, and the other part is the algorithm, and this is what we want the machine to learn. This is how we want to machine to learn, and the third one is training. So with we have data and we have algorithm. We need to train the machine to learn the knowledge of the data. So just like we have a child and he don't know everything. So we need to train. He needs to go to the school to study and we need to train for more than 10 years to be adults. So this is the similar thing for the machine learning. We need to train it, and after training, sorry. Okay. After the training process, we can test the model. The testing here means that we can select because some models are trained well, but some models are maybe not trained well. So we need to select the best model to use to our prediction for a specific task. So and then we can evaluate the well-trained model, and finally we can use a well-trained model to make predictions for a specific task. So this is machine learning. And here is a picture to show you what are the relationship between machine learning and artificial intelligence AI. And you can see machine learning is a subfield of the AI, and in recent years, there are many kinds of algorithms in machine learning, and one of the common used and powerful algorithm is the artificial neural network, you may know deep learning. Deep learning is kind of is using artificial neural network to learn features from data. So artificial neural network is a collection of nodes, a collection of neurons. The neurons is like it's also called nodes. It's a collection of neurons. The neurons is looks like this, and it has similar functions like the biological neural net biological neurons. So it has the inputs and the outputs. So it can give or output depending on the inputs. So there are a lot of applications of machine learning in cosmology and astrophysics. And here I just asked the ChatGPT to give me a list of the applications. So you can see in what range field of astrophysics and cosmology there are many applications found on the gas classification of galaxy and stars, and discovery of exoplanets, and even the detection of dark matter, and image analysis, because there are a lot of image in the observation of cosmology and astrophysics. So for example, the convolutional neural network, CNN, is a powerful tool for image analysis. And there are also redshift estimation, data compression, and there are a lot of other applications. Oh, okay. So next, this part I focused on the one of my research is focused on the foreground subtraction using machine learning. Let's say this figure is a very famous figure of the microwave background radiation. Is a is the temperature fluctuation of the universe at a very early stage. But you know, it's not easy to obtain this figure because there are a lot of foreground and noise in the observed data. So it's a complex process to obtain this figure. And for example, this is a simulated cross signal, cross CMB, and this is a simulated CMB signal plus the foreground, because there are a lot of foreground between between the CMB and the Earth. So the observed CMB might be contaminated because the existence of the foreground, and you can see with the foreground vary, and the foreground vary with different frequencies. So we need to remove move this unuseful foregrounds. So this is a big challenge for the analysis of CMB data analysis. So here we use the machine learning method to deal with the to subtract the foreground components. So the main idea is to using UNet encoder. It looks like a U, so it's called UNet. And the first part is a decoder. Decoder means that we input and the output of each layer decrease along the increase of layers, and the right part is called a decoder. Decoder is the inverse of the encoder, and with the layer of with the layer increase of layer, the output will increase. The size of the output will increase. So we expect to input the contaminated CMB observation and obtain a clean CMB signal. So this is the main idea. And you can see there are connections between each layer of encoder and the decoder. So this connection is very important for the computer simulation, and it will used in many tasks, both in cosmology and machine learning science. Okay, this is a simple result showing that if we can use machine learning to subtract the CMB foreground component and obtain the CMB signal. This is simulated CMB signal, and this is record CMB signal by the machine learning. So you can see that its residual is quite small, and we plot the angular power spectrum of the CMB signal. You can see that it was recorded very well for both large scale and small scale. And this is the temperature components of CMB, this one is for the simulated data, and we finally use apply the well-trained model to the Planck CMB observations, and this is a map of obtained by a traditional algorithm called commander foreground plane called commander. This algorithm, and this is obtained by Planck collaborations, and this is a map obtained by our method, by the machine learning, and you can see the residue between these two maps. There are still a lot of information between these two maps, but if we calculate the power spectrum of the CMB, you can see that the power spectrum is much similar with the Commander method, the CMB obtained by the Commander method. So this shows that we can sure use the machine learning to recover the CMB signal. And this is for the temperature CMB and CMB temperature map. And we can also use the pipeline to the polarization map signal. And this is the simple results. You can see the upper panel is the result of machine learning, and the lower panel is a result of a Commander algorithm. You can see that these two are very similar, and so this shows that machine learning can not be used to the component components of CMB polarization signal. Okay, this pipeline can be also used other sky survey data like 21 centimeter 21 centimeter signal. You know, 21 centimeter signal is very faint, and there are a lot of foreground in the line of sight between the Earth and the source. So the final observed data might be very contaminated by the foreground, and we cannot say if there is signal in this observation. So this is a very big challenge for the 21 centimeter cosmology. And similar, use the same model, we can obtain the 21 centimeter signal by input the contaminated data. You can see this is a similar structure of the CNN, and the output is a cross signal of a 21 centimeter signal. And this is just a similar similar test with a toy model, and you can see this recovered 21 centimeter signal is quite similar with the simulated formation simulated target truth. So and we are using this method to explore more details of recovering 21 centimeter signal to see if we can really to recover the 21 centimeter signal. And yes, this part I want to focus on the parameter estimation using machine learning. You know, parameter estimation is a final step of research of cosmology and astrophysics, and because we need to know, we want to measure the model parameters of cosmology model and some astrophysical model. So the usually method we use is the Markov-Chain Monte Carlo method to obtain the posterior of the parameters, and the Bayes inference and the Bayes sim is used here. You can see this is the lattice function, and this is the distribution of parameters, posterior distribution. And so in this framework, we need to sample the parameter space to guess the true parameters, and to obtain the true posterior distribution. And for each sample of the parameters, we we need to calculate the likelihood and to measure the difference between the observational data and the simulation model. But this framework has may not work well for some complex and resource-consuming models because for some models, the likelihood function may be intractable in practice, and the simulation may also consume a lot of time, and so in this currently a lot of people are finding a new a better way to make parameter estimation. So one of the approach is for the likelihood-free inference, which is we use to train estimator to obtain the posterior of the posterior distribution of the parameters. And there are mainly three ways to train estimators. And one way is to train estimator to estimate the distribution of parameters, and it's a joint probability of density between theta and the t. The t here is you can consider as a summary of the observation data of the observation data itself. And the second one is to train estimator to obtain the distribution of the parameters, and the third one is to train to learn the likelihood of the to learn likelihood by giving a parameter. And we select the second one to design our estimators we are using narrow density estimators. The narrow density estimator means that we are using artificial neural network to train narrow density estimators to learn the posterior distribution of the parameters. And the main idea is of the narrow density estimator is to learn a mapping between the data space and the parameter space. So for a specific model, we can obtain the observational data by giving a set of parameters, but we don't know the exact true parameters of the observational data. So the estimators here just learn a mapping between the data space and the parameter space. So this makes we can obtain the parameters by giving observational data. And here we developed a code called Coffee, and there are three estimators here. ANN artificial neural network, and the second one is the mixed density network, and the third one is the MN mixed neural network. I will briefly show you these three estimators and show you the structure of the Coffee to how it estimate the parameters using artificial neural networks. The first one is the artificial network, and you can see there are input layer and the hidden layer and output layer here. And the input layer is we input the observational data to the input layer, and the information passed from the first layer and to the second layer and to the third layer and finally we get output. The output is the information we want to know about the distribution of the parameters, and each node is narrow, and the narrow function of narrow here is to give output by using the input. So for the AI here, we the output is the cosmological parameter directly, and you can see that we input the observational data and output the parameters theta here, and this is for one data set, and this is for multiple data set. And the second estimator is MDN. MDN, the main idea of MDN is that assuming we have a parameter with the distribution like this, like the green areas, and we want to find a model to best fit the distribution, like the dark line. And the idea is that main idea is that we can fit the best model by using several Gaussian distributions or several other knowing distributions. So this is the main idea, and this is the probability distribution of the parameter. And the key here is the number of component. The components is the polynomial here is the for Gaussian distribution. And so sorry. So the network here input of network here is observational data, and the output is the parameter of the matrix model. So if we know the parameter of the matrix model, we can opt the posterior distribution. So this is the main idea of the MDN. We can also use the beta distribution and as the components of the MDN. But this network has shortcomings because they will not work well for parameters with truncated distributions, and I will show you later in later slides. And we intend this method to be the third one. The third one is called MNN. The difference between the third one and the MDN is that you can see for the MDN here is output is the coordinate matrix of the mixed model, but for the MN here is we can directly output the cosmological parameters, and so this is a difference between these two methods. And here is a detailed comparison of these three estimators. So I just show you the difference, and there are many details here. I don't want to, so I don't show you the many details. So if you want to learn, you can check it. Okay. And for the, for the training set, we have labels. The label is the cosmological parameters. So the parameters that we need to sample the parameter in a parameter space, right? And there are two sampling methods here, and the first one is to sampling the parameters in a hypercube space, and you can see the red one is the posterior distribution of the parameters, and the dots here is the samples we obtained of the training set. And the second method is to sampling in a hyperelliptical parameter space by using the correlations between any two parameters. So this is a more efficient way to sampling the parameter space, and we can using smaller training sets to obtain a good posterior distribution. So here is a framework of the coffee code, and you can see we input the cosmology model, and the model here can be any kind of model, and we can set an initial parameter space, and it will the training set will be simulated automatically, and we can here we add the error. The error is caused by the observation, and the training set will be processing to and after that we can build a model to train it. After the training process, we can get the well-trained artificial neural network model, and finally we can input the observational data to the model to get the estimation, and the estimation we can get finally we can obtain the posterior distribution of the parameters. And the figure here just show you how it works. You can see there are several estimations here. For the first estimation, I want to note you that the red area is initial parameter space. So this is a Bayes the parameter setting. So you can say for the first step, the coffee cannot obtain the true posterior distribution, but with the increase of the estimation, it will find the true posterior distribution. So finally, it can find the true posterior distribution, and this is the link of the public code coffee. Okay. Because there are many hyperparameters in the neural network, and we need to find a set of hyperparameters that is optimized for the specific task. So we need to tune the hyperparameters to find the best model, and we usually to check this with using the loss function. Okay, we test we using some simple data sets. Here is we test we using the supernovae data, and we obtain the results, and you can see that these three estimators can obtain the same results as using as the MSMC method, and we also test this method using the angular power spectrum of the CMB, and you can see that it can also obtain the similar distribution used as the MSMC. But why these results are the same, are almost the same with the MSMC method? This is because the data we're using here is Gaussian distribution, and that means all data here is Gaussian data, and there's no extra information from machine learning to extract. So this is why the machine learning result should be the same as the MSMC method. And finally, we extend the coffee code to deal with 2-dimensional and 3-dimensional data, because there are a lot of observations as 2-dimensional and 3-dimensional data. So we extend these 3 estimators to using the convolutional neural network CNN. And we test with using the observation of 21 centimeter observation. So for the 21 centimeter observation, we can get a lot of information of the universe, because it's a observation of 3-dimensional data. You can see because of the expansion of the universe, the wavelength of the 21 centimeter was strength to different wavelengths. So we can have a measurement of the 21 centimeter to be a 3-dimensional light point. So recent research show that using the machine learning methods, we can obtain a better estimation of the parameters. For example, here we constrain the model, the parameters of the realistic model, these two parameters, and they are using the similar structure of the network as the coffee. And this is a structure of CNN, and this is a structure of fully connected network. And the input is the three-dimensional Litecoin, and the output is the parameter directly. And this is their results. You can see they find that the result, the error of the parameters obtained by machine learning is slightly smaller than the traditional MSMC. And we also using our method to constrain these two parameters, but we attain the coffee to deal with three-dimensional data, and this is similar. This is temporary results. You can see that our result is much better than the previous one, and the error of the parameter is almost 5 times smaller than the traditional MSMC method. So if this result is correct, that means we can capture more information from the three-dimensional distribution of the 21 centimeter observation. So so maybe this maybe the CNN can be a very good tool for parameter estimation in the future. So this is the product of parameter estimation. And here I want to summary about my talk. First, we applied the machine learning to data analysis of sky survey experiments to recover signal from the contaminated data, and we applied it to CMB observation and 21 centimeter observations. And second product, we applied the machine learning method to constrain cosmological parameters, and there is code we developed that and the results show that more information can be extracted from the observation than the traditional MSMC method. And this method is much faster for some complex implicit complex models, and this is the advantage of this method. And imagine that because we have a wealth of data in cosmology and astrophysics, so and big data is necessary for machine learning. So I think the machine learning can improve the research of research in cosmology and astrophysics in the future, and maybe it can play an important role in the future discoveries in cosmology and astrophysics. And just imagine that maybe in 100 years later or even longer, we may have a AI physicist that able to tell us the problems of the universe that we don't know. For example, what is dark matter? What is dark energy? So this is the picture of the future. But it's just a dream, but it's worth putting. It's my talk. Thank you. Thank you so much.
Yeah, thank you very much for the nice overview of machine learning methods in your astrophysical data. Are there questions for Dr. Wang? And I would like to encourage the online participants to use the Q&A or to raise their hand, and we will give them the right to speak. Surab, please. Microphone is coming from the other end.
Thank you very much for your talk. So I've often heard this analogy between the neural networks of machine learning and the human brain, and I always wondered how close they are to each other. Now you said something that I've never heard before, that a neuron also has input and output. Is that determined for certain that it also has the similar structure of input and output, where input channels only bring information and output only takes information out for a human brain? Is that true?
Uh, uh, eh, uh, Let me answer your question. Can you repeat your question briefly? I think.
Maybe the picture we need is the one the previous one where we had a picture of a neuron.
Yeah. This one?
So is it so that from one side we have information coming in and the other side information goes out? Not on the bottom picture, but on the top picture, the one of the neuron.
This is just the neural of the neural of the neural network and
I'm now asking a question about neuron in the brain.
Mm.
Is it also structured like that information goes in and then goes out separately on a separate channel?
Yes, for the neural in the brain, it can give actions based on the action of the input. But I must to say that the neural in the neural network is it just similar with the neurons in the brain. But I'm not sure if they actually is the same, has the same function. Maybe this is problem to be addressed in the future.
Thank you.
Other maybe more astrophysical questions from the audience? Or I think, will you read the Q&A? Thank you, Donovan.
Sure. There's a question online from Sambatra. Have you considered using flow-based models like masked autoregressive flow as a density estimator instead of MDN, or a combination of the two?
The combination of MD and what? Okay. Okay. For this model. Yes, MAF is it also can be used to estimate parameters for parameter inference. We didn't consider the MAF here because we think that the function of MAF is similar with MDN, and it's also based on the I think the main idea of MAF is very similar with MDN. So because they are also using the base distribution, such as the Gaussian distribution, to make sure the distribution of the final posterior distribution. Yes, this is my thought. Thank you.
Thank you.
On?
Jens, please.
Thanks. Well, actually, I raised my hand previously, and then Francesco asked for astrophysics talks, and then I lowered my hand again. Because I have another question on this transparency where we had the neural network. I think it was number 8 or something like that.
What do you mean?
Okay, well, we can also use that one. Okay. So my question is simply, why don't we have vertical connections on the hidden layers? So can't they talk to each other, or?
Is this? Oh, sorry. Is this one?
No, number 8. I think it was
Number 8.
okay. Yes. So on the very right. So can't we have something like vertical arrows up and down in the middle hidden layer? Can't these vortices talk to each other, or is it?
You mean connection between up and down?
Yeah.
No, no connection between the up one and down, because they are the same layer, and they only connect with the layers between in front of it or the follow layers.
Okay, so only different layers can talk to each other.
Yeah. Only the third one and the second one, only 2 layers between 2 layers.
Then I have another question on your fitting procedure with the various components. I think maybe something like or something. Further. Go further a few more slides.
This one?
No, you had your fitting of data with various Gaussian components. Okay, so this one can do it as well. So here you have some fitting for loss functions sitting in there, and you have the number of components, which is capital K. Is that an input, or is that also determined by the machine?
The K is the number of components. The components can be, for example, the Gaussian distribution. That means, for example, if the K equals 3, that means there are 3 Gaussian distribution, and the parameters, for example, the parameter omega here and the mu sigma here is the parameter obtained by the neural network.
I understand that. My question simply is do you tell the machine what K is, or does the machine by itself determine most?
No, we don't tell the machine what. Oh, okay. I mean, I know you can. The key selection of key is by human beings. So you can use 3, 2, or even more components. That is on the. But usually we need to use more components because the distribution of the parameter may be non-Gaussian. So for example, we need to use 3 or 5 components.
Okay, so but you choose the number.
Yeah, I choose the number.
Then I have finally maybe a funny, challenging question on your very last slide. So this future artificial machine, how do you know that it has 2 legs and 2 arms? Thank you.
Okay. This is just a big picture of the future. So there's a long way to get to open AI physicists. So this is just a dream.
Okay, maybe this last question is a good hint to stop the colloquium here. And let's thank very much our speaker. Thank you very much, Dr. Wang, for the talk. Thank you very much for the online and the physical participants. And we hope to see you again next Monday, where we have another very exciting talk. Thank you very much. Have a good evening.